Have to pardon me, I'm still trying to get some stuff set up here. Huh? Why does this look weird? Hello. Hello. Okay, so today this is going to be a little bit of a co-work stream. So I will be working on this dim here paper that I'm trying to write things out on. And we'll play some music, and there's a good chance I will be bouncing back and forth looking for other stuff. Probably pulling books off of shelves and looking for stuff. So I'll be in and out of chatting. So feel free to swing by to vibe. So Potato is having his first day back at the doggy day camp after his surgery, and apparently is going flippin' nuts, which is perfect. That means, yeah, that means he'll sleep tonight. This is his first time going back in like months, so he is super, super happy. Before I get started, I will point out we have this Trevor Project donation link. Please feel free to either donate directly here or through their through their primary donation mechanisms. This is done through Twitch, so I do not see any of the money that gets donated through this method. Twitch does not take any money out of the donations. It all goes to the charity in question. So so if this is important to you, please feel free to donate through here, donate through them. Just kind of want to raise the knowledge, the awareness of this. It's a fairly well-known charity. They do mental health support for LGBT plus youth, and it's a good thing to do. So they help people. So we're doing a little support for them. So yes. Right. So, with that out of the way, let's play some music. Bring up the volume a little here. Bring up the volume. Oh, volume is max over here. Okay. Cool. Let me know if the music is too low or getting a little too out of hand. There's some wacky parts when we'll jump ahead, but and I have another let's see. Sorry, there's another one I want to put. Like, can I? Save to a playlist. Okay. And now, what is it? It's hold on. Oh my goodness, what's the name of that stupid music? No. Yeah. This is my driving through the woods in the middle of autumn music. All right. Well, let's get to work. I'll remember the other music that I'm gonna play later. Okay. Qualitatively and functionally describe. Experienced by radio. Describe. CRIB. As was. Um, as um, as of descriptive model. Of um most functional of uh, um, applicability to particular problem set. I don't like that verbiage, but okay. I'm gonna take out the I. The method described here. Loss field method. Okay. To okay, we'll figure that piece out, right? So subsection biometric by second. Okay. So this is gonna be the hard part that we're starting to do here. Okay. So which is nope. This one. I want to add. Does this have a acknowledgement? No. This doesn't have a insert. No, I'd like to add a file. No, I want to do a it's called a bibliography file. How do I add a .bib file? Or count no, insert math cross reference citation. Well, we don't have a bibliography to cite from. Let's see. I need a bib file. I need a bib file. What's to reference to? Bib. Use bibliography generated by bibtext as a WBL file. Bibtext documentation considers. Okay. Okay. Oh man, I hate latte. Boy. It definitely has its positives, but it man, it's overly complicated. Let's see. Yeah, I would like actually BibTeX style. Okay. Um, helpful. Very, very helpful. Let's see. We want bibliography in overlay. We'll figure this piece out later. Man. Okay. Let's just go back to here. And we're gonna throw in a citation that's gonna be filled in later. The authors have a drive a radar cross section. To be used for monostatic HF radar. Pretty sure monostatic is just a word. Monostatic HF radar. Ground wave radar. That is concerned with I know how to spell. It's fine. It's fine. Everything's fine. Everything's awesome. Everything's fine. With spheric noise from from backs yes. Concerned with probably just like this. Concerned with noise from ionospheric backscatter from the skywave propagation mode. Ooh, is this the loud one? Yep. Get ready for a loud bang. There's gonna be a loud bang in the music. There it is. Loud bang. Okay. Do this, they modify the monostatic radar equation. Was it begin equation? Begin equation. Okay. That was it. Frac T sub T G sub T. Missing argument for end. What? Huh. Well, we'll see what happens. History, G sub R lambda. Is it caret or is it star? I think it's caret squared over 4 pi cubed r to the 4th L sub s sigma. Let's see what this actually looks like. We recompile this. Okay, good. To account for the volumetric nature of the scattering within the ionosphere. Just say much more. Account for the volumetric nature of scattering in the atmosphere. Okay. This becomes again Gibbs equation. There we go. PT equals frac P. Oopsies. I'm sorry. PR. This is the received power equals the transmit power times lambda squared over 4 pi cubed L sub S, that's the losses, times geez, what is it? INT? Is that it? What's integral was it's been too long since I've used Logitech. Integral. It is INT. Ugh. I'm a silly little goober. INT underscore. Let's see. We've got delta. Can we do this? Oh, let's say this way. Delta V R comma theta comma phi. Okay. What does that look like? I don't know if I did that right. Dang it. Okay. So it needs to be int. What happens if I do this? This. Recompile? Is that just gonna be? Yeah, it's just gonna mess up. Because delta. Okay. How do I do this? How do I do this? How do I do this? I need how do I do V okay, hold on. Integral int okay, lim. Okay, so it's curly cues. So if I do like this, what does that do? There we go. Now we got it going. Frac GT as a function of theta and B times GR as a function of theta and B over R to the fourth d sigma as a function of R comma theta comma phi. Let's see what that does. That look right? Let's go. Okay. Okay. Here. Let's see. Well, I'm glad that was an appropriately timed bang in the music. Okay, so what's going on here? So our received power is our transmitted power times the wavelength squared over 4 pi cubed. That comes from the fact that we are looking at a surface of a sphere expanding out, right? So for anyway, so 4 pi cubed times ls. Ls is the losses that occur within the overall system, right? And then we're integrating over some small dv, which is at some distance r, some angle theta phi, covers some angle range theta phi, right? Within the kind of view of the radar. GT is the transmit antenna gain, which is a function again of the angle from the antenna to where you're looking, and then the receive, which is a function of the angle where you're looking, over r to the fourth, because we have 1 over r squared loss factor on the way out and on the way back. and we are integrating the sigma, where sigma is your radar cross section at a specific point, r theta phi. Okay. Okay. We will need to make some modifications to match the geometry of the high dive high dive experiment. Mental setup. Experiment. Which better approximates a bistatic radar than a monostatic one, as we are not concerned with backscatter anymore. Monostatic one, you're not concerned with back. And we are not concerned with backscatter anymore. Okay, so so here's where. Okay, so bistatic radar range equation. Okay, let's see. Okay, so okay. Cool. Power density S2 and the effective area of the receiving antenna. Usually AF is GR lambda over pi, right? After substituting the receiving echo is sure the target echo noise. But that's the standard. Where's the bistatic radar equation? Range equation. Effective area, the total echo. There's a noise type N of various nature, most common sources include thermal noise, man-made noise, background noise, cosmic noise, blur to blur to blur. Okay. That's signal to noise ratio. So let's use to determine the RCS. That's not really what we want right now. The direct path interference, blah 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 blah. Okay. Power density at the target. No, we don't. Okay, as soon as we're reflected, right? So the power received by the radar determined by the power density S2 and the effective area of the receiving antenna. Sure. Okay. Okay. So, to do this, we by static radar. It's interesting that that's the only difference there. Okay, so the bistatic version of the volumetric range radar equation becomes okay, hold on. Okay, BECOMES. Okay, becomes all right. This is where we're having to fly by the seat of our pants here. All right, so we're gonna start with this, and then we're going to modify it. So PR fraction. Okay, so we still have the transmit power. That's fine. Lambda squared over 4 pi ls is fine. But now here's where things get a little wonky. Delta V, so our volumetric area that we care about doesn't really matter, right? It's the same volume, right? It's the same volume regardless of which side you're looking at. So we'll put a pin in this. All right. So it's going to be theta T B T, right? Theta R, because these are now different angles. One of them is for the transmitter, one's for the receiver. Our R to the fourth becomes RT squared, R squared, right? Because we have different ranges. The sigma. What should we look at? We should look at everything from the point of view of the receiver is what I'm thinking. Right? The point of view of the receiver is really what matters. So R theta R phi R. All right. So that means we are integrating over BR. Right. And this is over RR. Right. Right. Does that really make sense? That would allow us to pull out the transmit side of things. Right? Because then that's interesting. So I'm not sure I like this. 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 Because I feel like we need to integrate over both, right? So by integrating, I'm kind of summing up all of them, all of the. All right. Let's think about this for a second. Right. Because we are interested in essentially the total power there. The total power that's the transmitter places into the volume can be thought of as a volumetric transmitter, right? At that point. Okay. So to find the total power, oh, wait. Hold on. But theta T and theta R aren't really independent, though, are they? No, I guess they are, because... Right. Hold on. Let me think. Yeah, because otherwise it would be like all the power is at all of the locations. And that's not right either. So the thing that's going on is theta T and theta R should not be independent from each other, right? Okay, hold on, I'm thinking. So my gains, right? My gain geometries are not changing over time. I'm not using a swept beam. I'm not doing anything fancy like that. I just have my antenna gain geometries are both static, right? What's not static is, so what that means is, right, there's the reflection pathway. So the transmit pathway to any particular point, theta phi, is just going to get a single, like, all right, hold on. So each point theta phi is going to get a specific amount of power that is g of theta phi. Oops. Forgot there was another bang there. Right. G of theta phi times power, right? Because that's the percentage of the power that's going to that one spot. Then the received power sorry, this is really bad time for the music to go nuts. All right. Let me try drawing this. Let me see if I can show drawing this too. Okay, let me see. Tell me if this makes sense to you. All right. So, right, we are looking at this spot here, right? Man, sure would be nice if someone didn't chew my pen or my tablet. Right, so we're looking at some. We're looking at some volume like this, right? That I hate drawing with my mouse. It's so bad. Right, so we're looking at some volume like this, right? Down. Pretend this is. Okay, pretend that's a valid cube or square prism, whatever you want to call this, right? Whatever, it's some volume. Doesn't actually really matter the shape. Okay. From our transmitter, right? Each point here, so our transmitter, say, has a pattern that looks something like this, right? So this is kind of our power ratios, right? This is our gain. So this point here is going to have some angle from the normal, right? We have some angle theta phi, right? That's going to point here. So it's really what we're looking at is this amount of gain at this point, right? That's why we're going through all of the angles here. On the receive side, right, we also have some pattern that looks kind of like an oval, whatever you want to call it, right? And then we're going to have our primary pathway through the receive side, which is going to have some receive gain times the power that actually reflected off of here, right? Minus all the propagation loss, et cetera, et cetera, et cetera, et cetera. Right. So the question is, do I need to integrate? Right, because when I'm doing the integration, I'm integrating not from point of view of the particle here, right? I'm not integrating over this volume. I'm integrating over this volume, right? So imagine this is a sphere. I'm integrating over this volume, not over this volume. So what that means is there is only one angular pathway for each point between my transmitter and my receiver. That means that my angles are not independent of each other, right? So how do we handle that? Because that makes it a lot easier, right? That makes life a lot better. So now what we're asking is, we have a triangle. So we're asking, how is this angle related to this angle, right? Kind of. That's the two-dimensional. Yeah, right. This is a two-dimensional version of it. But again, it's really three-dimensional. But regardless, we only have one vector, right? Because we're looking at the simultaneous vector from our transmitter to our point and from our receiver to our point. So we're looking at those two vectors, right? And those two vectors are only going to intersect for specific theta and phis for both the transmitter and receiver. Right? So, how do we think about this? So how do we think about this in 3 dimensions? I guess we could tie the two together in some way. How do we do that? 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 It's a little weird because like the 0 for the various hold on, right? Because the 0 points for these are the normal to the antenna, right? So what you're doing is you're going, oops, going like this. Ugh. I don't know why it sometimes makes a line and sometimes doesn't. You're going like this and like this, right? So this is straight. This is normal to the this Z direction, right? Is perpendicular to the antenna itself. And then you have an elevation angle and an azimuth angle, right? And then that's going to give you right to this point here. Okay. How are we going to tie these two together is the question. That's really the question, right? Because we want to integrate over at once. What is the relationship that those two vectors have to each other, or the angles of those two vectors? What is the relationship that those have? What's the relationship that those have? Right. So, sorry, I'm thinking. Oh, what's the relationship that those two have? What on earth is playing? Okay. It decided to go on to something else. I would like to play instead of that something else. Guitia, yes, by Peter Gundry. There it is. There it is. There it is. Album, yeah. Go to the album. This is my other creepy music that I enjoy when I'm trying to think math. I am going to be right back. Because I need to use a latrine. Be right back. All right, we will be right back. All right. Yeah. Yeah. There we go. We're back. We're back. Why can we not see? Okay. Cool. Let's play Goichia. All right, cool. Okay. Okay. So, what is the transformation really that goes from this what if I'm thinking of it wrong? What if I think of it from the point of view of the target point? From the point of view of the target point, I only have one transmit and receive pathway. So it's the direct line path from that point but then I have the I have to deal with the mapping of the antenna pattern, so that doesn't really work very well, does it? Because the whole point of it is the antenna pattern piece, right? That's the whole reason why we've got the angular issue that we care about. Yeah, I like this. This is a really good album. It's got some weird and creepy music on it too. It's great. Let me think about it. Let me look at this. Let me look at the. Hold on. Let's go from this to this. Go back to this over here. All right. So if we look at how the old version works, right? We're just integrating once. But you have the equivalence for transmit and receive, so makes sense. Oh, wait, hold on. Hold on. I might be being really stupid. No, where's my... There's a fair chance I'm being really flippin' stupid here. All right. What am I thinking, right? Right, so we're looking at the vector from... In 2 dimensions, this will be easier, but hopefully it'll allow us to translate to 3 dimensions, right? So the question is, what's this angle compared to, say, there's some old school geometry right here. Right, so we're looking at the difference between this angle compared to this angle, right? Right. Shouldn't these be complementary angles? Right, because if you were to extend this out, oops, extend this up. Pardon my bad drawing ability here, right? Oopsies. All right. So in this case, this angle should be the same as this angle, right? No, because they're not parallel. Of course, it's not gonna be the same. Okay, no. Here's what we do know. This is the complement of this angle, right? Right? We know that that's the complement of that angle. Okay, so we've got one piece. So we've got one piece, we've got one side here that's the same, right? Oh my god, I hate this stupid geometry. Okay. We've got this side that's the same, we've got that piece that's the same. That means what? Or that's the complement of this. So then 180 minus the complement. 90 minus theta, right? Is going to be shared. So it means 90 degrees are shared between these two. Right? That means there's 90 degrees left. That's the same length. That means, hold on. We don't know hypotenuse, right? All right, so we've got this. So we can say that the tangent of this angle, right, is so tan. So if this is phi, right? So tan phi equals opposite over s, right? This thing, this here, right? Which is actually our range, right? This is our r sub r, right? Our receiver range. Okay. Oh my god, this is so. Okay. Sorry, I'm being so silly about this. All right. Right. So we know tan physics, and we know that R, right? Okay. I need to grab a whiteboard to do this because I need to be able to scribble a little faster. Oh, I really, really wish I had my pen still. When's that supposed to come in? Sorry, I got distracted. I just got distracted by someone. Oops. When's my pen supposed to get in? I want my pen. July 19th to 23rd. No! Oh, that's awful. My pen. We could do this on the other computer if we really wanted to. If we really want to. She removed that from my... Okay. Oh, those are arriving today. Cool. I got a couple more shelves for my server rack. Yeah, I ordered one, but it's not coming in until the 19th to 23rd, which is really annoying. It would just make life a lot easier than trying to do it this way. Okay. Sure. Whatever. Yeah, I might... I might go run out to the what's it called? The Best Buy to see if I can get one there anyway. Just because I don't have a duplicate in case Potato decides to eat another one. Right. I feel like I'm being so stupid because I'm so close to this, right? Let's see. We know this. Okay, so we can find the opposite. We can find... Okay, so that allows us to find this here, which then allows us to get this angle. Okay, cool. We actually have it. We've got it right here, right? Since we know phi is the complement of this angle here. Right? Then O is our range to receiver times tangent of 90 minus this angle, and then once we have opposite, we can do you know, cos or sine of this angle is opposite over adjacent, right? Which is RR. So okay. Sure. So we can get those angles. What's it give us? What was I doing? What was I actually doing here? Right, we need to convert from this angle to this angle, right? So let's say this is alpha and this is beta, right? Because the old version was integrating over beta. Okay. I might be overcomplicating this too much. What if we just did it? What if we just integrated it twice and then divided by the power, the total integrated power there to normalize it? That might be an easier way to do it, right? uh Because the old way integrated over that, right? So yeah, the way you can think of this also, right, is this is kind of a, if you were to project this to flatten this, you could think of it like a circle. And now I've got two angles. It doesn't quite work because it's, yeah. One's angle. That one's down. Where's. Right, if we were to look this end on, then you're looking at an end on, the center is there, and then you have one angle which is giving you this distance, and one angle is giving you this distance. Doesn't really help. Okay. Um, All right. When I integrate the transmitter side, I'm providing essentially a energy power to each point in the volume, right? And then I'm looking over that volume from the receiver side. And I'm seeing kind of the overlap of. So I then have a volume distribution of power. I'm trying to receive over the volume distribution. I'm trying to angle my receiver over the volume distribution of power. Right? It still feels like these should be tied, right? Still feels like these angular, because they're each point in that volume has a single theta and phi value for the transmitter and a single theta and phi value for the receiver. Therefore, there's necessarily, because there's 1-to-1, there's necessarily a transformation between the two. Right. This feels actually really easy, and my brain is just straight up not working. Man, I know there's a direct and easy way to do this, and my brain is not freaking working. Where would I have this? Let's check a electrodynamics book. It's got to be in here, an electrodynamics textbook. It's wavefront distribution. No. Observation. No diffraction. No. We need Fresnel diffraction, Fraunhofer diffraction, Kirchhoff interval. Integral, I should say. See, scattering, that's kind of what I want, right? I feel like there should be... Right. Okay, so... Transmitter radiation pattern depending on the azimuth angle for target, whereas the receiver pattern and azimuth elevation angles towards the target from the receiver position. Right. Result of the application of azimuth transmitter radiation pattern to the range. The type alright, so the result percentage of azimuth radiation pattern. So azimuth radiation pattern of the transmitter antenna influences the performance of the passive radar substantially. A simplifying assumption on the omnidirectional azimuth radiation, often applied when no detailed information on the transmitter is available, can lead to an overly optimistic performance prediction. Right. If you don't know what the transmitter is looking like, and so you make an estimate, but your estimate's wrong, then your receive power is going to be wrong. That's fine. If radiation patterns are available, they can be easily, and you have to calculate the RCS resistance. Okay, fine. Influence of transmitter elevation radiation patterns. Influences the elevation pattern and detection characterized by passive radar. Most popular types of transmitters used by passive radar, such as radio and television, are preferably placed on high masts, buildings, or mountains to provide better coverage. Receivers are typically placed on the Earth's surface. Therefore, the usual practice is to focus the transmitted power in the elevation plane in a narrow sector. Because the transmitters are often placed relatively high, the elevation radiation pattern are usually tilted upward or downwards, typically by 0.5 to 1 degree, so transmitter, quote, looks towards the ground. Antennas used with radio or television transmitters are usually constructed by stacking several radiation elements vertically. Okay. An example of a theoretical elevation pattern is shown. Sure, it was assumed radiation, blah, 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 blah. Values usually provided by broadcaster. Okay, sure. Again, several dBd or dB with respect to dipole antenna for FM radio, up to 18 dBd for television. Let's investigate the influence of transmitter antenna elevation patterns on the passive radar. Figure 2.14 shows the elevation cross-section detectable RCS in all cases. The same value of EIRP was assumed. The only difference was the shape of the elevation pattern. The horizontal axis corresponds to. This shows the detectable. Influence of DPI. It's not really what I want. They're just saying they're different angles. I know they're different angles. Thank you. Reference with respect to transmitter and target. Sure. So reference signal X sub RT can be modeled in the following way. X sub R equals a ref. Has two components. One is to transmit the signal directly from the transmitter. The signal is multiplied by a complex radiation pattern. The reference antenna. What email did I get? Hello? Okay. Spam mail. Don't care. Don't care about the spam. Okay. Or to remove the reference signal from the echo. Right, that's. Ugh. I'm looking for. Does this have a volumetric target? Let me look in the index here. Spanky. Does not have volumetric. Not the ambiguity function. Okay. Mm-hmm. Okay. Well, that wasn't super helpful. All right. Three dimensions, right? So it's R theta phi at one point corresponds to a different R theta phi at that point. Sure. But we don't know the relative angles of the normal vectors is the problem. Right, because in reality, these are three-dimensional. So you have right? So you've got, say, like this, and this is your normal, right? And so your vector to target might be something like this here, right? Which is going to be a certain theta and a certain phi, right? So one's the azimuth angle, one's the elevation angle. So for a given volume, I'll have some sets of theta and phi that correspond to that volume, right? But those theta and phi's are off the normal, right? They're from the normal because it's how theta and phi are measured. Now, if these normals were facing towards each other, if we knew that, then we could start dealing with them. But we don't know that those are necessarily pointing towards each other. In fact, they're probably not. And we don't know the relative angle to them. Oh man, this is a tough one. And I don't feel like it should be tough. It's really bothering me. Right? Because ultimately, what we really care about. Let's try and get back to some baselines here. Um. The problem is that we're integrating over our delta V, but in this case the delta V, the theta and phis are the same because it's the same transmit receive antenna, but now we have different theta and phis, one for transmit, one for receive. So we can't just integrate it in over one set of theta and phi because that's not correct. Oh my god, why is this breaking my head? Come on, this is not hard. I'm gonna see something. It's not on here, right? Oops. Ah, damn it. Something I want. Wait, what? What? What has happened? There we go. Weird. Okay. So now if I go here and I look for... let's see here. Let's do this without doxing myself. Come here. Okay, that is not what I wanted. All right. Do they have any Wacom stuff? And tools. Will that pen work with it? And compatibility. No. One, two, Oh, that's incredibly frustrating. Uh, Porsche. Oh, I hope I ordered the right one. Okay, welcome to. Okay, welcome one pen. Yes. Be on Amazon. Okay, so this is so I did order the correct pen, but it's gonna get here until forever. Oh, jeez. Oh, I don't like this at all. Now I am most definitively just procrastinating. What is this? No, it doesn't have an eraser. Boo. Yeah, like that. Choose pro paper. Choose pro paper. Now I'm going down a rabbit hole for this airbrush pen. What? Distractions are us. On a side note, I don't remember Toys R Us. Man, that was great back in the day. Anyway, right. Well, my brain is wandering. So let's see what let's just do a little other stuff here, and then we'll I'll head out. I'll try and look at this later. Okay, so so if we go like this, here's what I'm thinking, right? So how do I do this? Oh no, all that tea is coming back to hit me. On. I'll be right back. 1 second. Whew. All that tea. Man, I need to make more tea now. Hey, Milty, how are you doing? I hope you are doing well. Come on, music be on. Turn this vehicle off. There we go. I hope you are doing super duper well. All right. Very nice, very nice, very nice, very nice. O and I. What's O and I? I feel like I should know that abbreviation, but I cannot recognize it off the top of my head. Okay. Sure. Ah, gotcha. Yeah. I saw you playing that yesterday. That looks like an incredibly intensive game. Okay. Why am I being so? I'm being really flippin' stupid about this right now. Okay. All right, but this is integrating D sigma. I don't like that. We're going to convert this to something else. All right, so we are going to convert because we want to do an integral over the entire space for the transmitter, right? And so that should give me essentially right. So I'm for now, here's how we're going to do this. Right. Here's how we're going to convert this. So we're gonna go like this. And we're gonna go. But it's not really. Oh my god. How do we do this stupid conversion? Oop. There's got to be a simple way to do this. Bloody thing. All right. So technically, so theoretically speaking, that is not the same music. I really don't like that. Just hops on to the next random thing after it finishes what's it called? After it finishes thingamabobbage. a thing. Let's see. What else do we want to play that might be nice? Let's go home. Let's see. Got that kind of thing. Now I'm kind of worried about what kind of wackiness it's gonna it's gonna suggest to me. We could always go for ye old. All right. Electro swing or this one. You this one. You get this one. It's not very Halloweeny. We need some better ambience music. It's a little silly. Hey. All right. How about this? Enjoy the dog walk. Thanks for stopping in. Tell Shasi hi. As long as we're going for things that are just distracting anyway. Mononov. Sergei Rachmaninoff. Which ones? Trying to remember which one it was. Is it Concerto number 2? I want. Here, let's. Concerto number 2 seems to be the more popular one, so let's. Here we go. Here's numbers 1 and 2. This is the closest thing that you'll get to the Russian steppe in music. Anyway, so what is my transformation function there? I'm so mad about this. Oops. And this is technically true. Right? We can just kind of do it that way. All right. I don't like that, but that's technically. Let's move on from here, right? Because right. So that is the volumetric. And in this paper, they do something weird, right? So they've got this, so the evenly distributes to the volume. Okay, but we know it's not. So, effective scatter volume, which is from for the antenna having elliptical elevation. If the resolution volume cell can approximate as R squared with R. Sure. Or delta R. Okay, I'll show this so you can kind of see what I'm working with here. All right, so this is the other paper that we're kind of taking this off of. Right, so we're saying right, so this is our integral over our volume d sigma, right, where sigma is the wow, this is a bit wacky. Hold on, I'm gonna drop us some volume here. I forgot that Rachmaninoff is also freaking insane. This is what's a nice, quieter, easier to handle set of music. So like I feel like electro swing, which is also usually my go-to, also kind of. Yeah, no, it's absolutely nuts. And I really enjoy Rachmaninoff. Like I said, it's like the Russian steppes in the music, right? It's this wild romantic style insanity. But if you're trying to concentrate on other things, it doesn't always work super well. Do something a little better for the background. Work. Lo-fi. Let's just do. The problem is most of this lo-fi crap is AI. Which is really annoying. I don't know if Lo-Fi Girl has committed to not doing AI or not. Yeah, exactly. It's because it's simplistic, right? That's the whole point of it. It's simple, easy to follow, kind of good background music, but that makes it particularly vulnerable to AI generation. Arg. Sorry, I'm doing really poorly at this whole work thing. let's see. No, not this one. Let me go in a different tab here. That's not gonna pop up. Okay, good. Okay. What is the one I am thinking of? Watch later? Did I put any of it in the watch later? Of course I didn't. Of course not. Why would I do that? That would be smart. Why would I do smart things? Okay, what have we got in this one? No. No, 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 no. Meh, 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 meh. Meh, 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 meh. I'm being an annoying, picky little person. Meh, 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 meh. Um. I thought I had saved more than that. Hold on, I'll find it. I'll find it. I'll find it. Not you. Not you. Not you. It's clearly AI. I think it's AI. Not you. Not you. That's probably not if it was streamed 3 years ago. It's not the one I really am looking for. No. There is a particular one for which I am looking. What if we did this one? Calmed by Nature is usually pretty good. Alright. This music just makes you want to jump around. So let's go to something a little different. There we go. Calmed by Nature is usually decent. They make a whole bunch of like background music things, but they've been going for a long time. And this one is tagged as no AI explicitly. So, oops. Don't worry about that. Don't worry about that at all. Everything's fine. All right. What was I just doing? Right. So the device set. Okay. Right. I was looking at. See where the. The. Um, I might edit this even a little more. So, bleh. So the way I might edit this more is I'm gonna switch this integral up to be right. We're gonna. That is dv. Right, because it's v as seen from R. Does that make sense? Yeah. Right. So delta V is seen from R. Right, because that's actually a triple integral over r theta r VR. Oops, and my sigma lost its annotation. There we go. Well, that's cool. I have to figure out what these are. I've got to figure out those transformation right, because at a certain point yeah, that's kind of messy right now, but at a certain point it'll do this. Okay. Okay. Now sigma is where is the S of a of the ionosphere at point r theta r VR. Is RCC at share point R? The angular dependency is based on the receiver. CIV on receiver dependency receiver EI, not E. Right before E except after C, something like A is a neighbor away. Our angular dependency is based on receiver. Oh, I still hate this. I still hate this. right? Because what's the transformation? Right? Because I feel like I can figure this out. Hold on. 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 All right. We're gonna have to do the desperate thing and start looking online. Okay. Um, what are they called? Internet transforms between uh mm, hmm, between antennas. Okay, antenna coordinate systems. Sure. That is not very helpful. Uh-huh. Useful coordinate transformations for antenna applications. What's this? IEEE is usually pretty good. Yeah. Make sure it's not coming up there. Okay, good. Yes. You are who I am. Getting. Let's see. Cartesian circle coordinate systems. Sure. Okay. Okay. Transformation between Cartesian and spherical. Okay. Polarization. Multiple antenna. Okay, Cartesian coordinates. Holy. I'm gonna start screaming indiscriminately at this. Okay, it's close, but not quite. We'll open another. Yeah, thank you. Mm-hmm. See, no, that's literally that same paper. Okay. Between. How do we do? That is infinitely unhelpful. Okay, let me look up here. Um, 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 let's, so I wonder if I have to convert through the two different paths, right? Here talks and directions first. Monastic art of the fourth construct. Right. Clean base set equation is. Oh, right. Or if you use the basic scattering coefficient, dB. Right. RT. Okay, so then angles are the same. Solar retain by projecting the same function to your transversal only corners of the features the rotation matrices. Oh, you have a rotation. For each theta t is ty. So the transformation of a transformation in the simple monostatic sense is a pointwise geometric mapping through a shared voxel coordinator R. This is an important conceptual shift for your original monostatic expression. The bistatic is closer to. Right. This scatter length can be dependent on the incident direction and on the scatter direction. Okay. The integration use one integration using to transfer. Okay. Over global Cartesian or just transfer. If scattering is coherent over the volume in the received field, it should be integrated first squared or then integrated the power directly. The equation of for incoherent locally randomized line. Okay. Right. Okay. Set of conversion functions. Set of conversion functions. Over. Highest one required variables receiver only angular pair. Uniquely identify scattering point unless you also specify range R. This is valid variable only if transmitter focus on the full receiver coordinate triplet. Okay, yeah. Refresh. Receiver look. Right. Okay, that makes sense. Parameterize the receiver coordinates. And R squared and the volume cancels out. Let's do geometric spreading. Receiver antenna goals. You find your basis. Then RT is R minus RT. The magnitude, okay. Transmitter look vector is, let's see, where that vector transmitter unique frame, UTA finally. Actual conversion is RS. See if you know something. What? What's that? Avoid. So unless you define it carefully, usually the volume is going to be cross section per unit volume. So that is okay. Position bubbles on the instant and scattered directions. Right. That is because. Okay. Yep. So the correct version of. And as a receiver circle integral. Okay. Linear furnace convention uses the standard circle Jacobian. Yes, it does. Interesting. That's the way to do it. Yeah, that's right. So that's gonna have a and this is also gonna have an R receiver range. Right. So we can do like this to make it a little more distinct. Okay. Hey, Gothic, how are you doing? We're just being a little silly over here. Good to see you. I hope your stream went well. I'm sorry I missed it. I feel really bad. uh Whoa, what did I do? infinite regression of streams. I'm just sitting here grinding my tiny brain out. Oop, phone call. 1 second, B's calling. All right, we're back. Okay. So. I guess technically that's the signal is the wrong term. It would more be an eta instead of a sigma. So this is, where'd it go? This is gonna be eta. Right, so that's the. See if I'm reading this correctly. Where that is the bistatic scattering coefficient. Carefully. Okay. Usually the volume form is scattering coefficient. For example, eta. Okay. With units like cross section per unit volume. So okay. We can do eta b. Here, A to B. Oops. A to B is the bistatic scattering coefficient. Now that one I actually spelled wrong. Okay, it's bistatic scattering coefficient. In such that sigma equals, actually it should be d. D sigma equals eta dv. Sure, yeah, that's their version of that too. This case, it'll be may not be only be position, but also instant and scattered directions is because receiver target geometry rather than only a monostatic look angle. Okay, depends on what's target and target receiver geometry. Right. So we could do that, right? And so then it would be RT is then also a function of R comma theta R comma B R. Okay. So yes. So now everything else is good, I think. Eta V of okay. But to dimensionally become a cleaner. Sigma dB for targeting sigma yourself carefully. Right. So, for what is okay? So S faces and RT transmitter look is then convert vector into the transmitter antenna frame. And finally, theta sub t equals cosine u sub t. The S cube. What's oh, what a pain in the butt. Just because I want to do into that. Yeah, cool. What if we remove this? Hold on. Bring it. No, of course not. Of course not. Of course, it's too big for this. Um. I kind of like that, but technically, why wouldn't that be okay? So here's my question. Here's my question. All right. So again, we're looking at transmitter, receiver, right? We're saying this is our or actually it would be like this is our coordinate system here. Could we shift? But we don't necessarily know the angular difference is a problem. Volume. So if we do right, because that's a particular point. Some of are to use the correct coordinates. Is there a way to do it that way? Yes. Given voxel point coordinates the same physical point, it'll give you a pointwise mapping between the coordinate system, but it's not a single global angular transformation unless range is included. Sure. Let's target. Okay. Then the same target point has two spherical coordinate positions, right? So equally, right? Rather than the equality between Cartesian points represented by two coordinate systems. So the core transformation relationship, given the receiver-centered coordinates, the mapping to receiver coordinates is R naught equals R plus S. So S is okay. Where QT is R naught minus RT. What's R naught? R naught is to convert ST0 into the antenna, into the transmitter antenna frames and the exact angles. There's transformation that, but not general. Okay. Compact wave transformations R equals R T. Okay. And then spherical. Where QT accounts for the transfer family, your receiver. Okay, for aesthetic, this means that receiver as that. If expanded and receiver spherical coordinates, right, and then you end up with that. This consists of a standard by static point structure where the denominator uses separate transfer receiver and relative directions. Bistatic references commonly write the received power, the GTGR, RTRR, and the bistatic cross sections signal B rather than the signal monostatic range angle. Okay. Useful geometric quantity of the bistatic angle, usually angle between the incident directions and the scatter direction of the target. Corresponding to a sign convention, one beta equals inverse cosine. Okay. This can matter because volume by static angle, polarization, and this transformation is pointwise and range dependent, not a simple angular mapping. Right. The centered and use the transform version of, let me see, because if we use a transform version of the transmitter coordinate system, right? I use the coordinate transform inside the integrand to evaluate the transmitter quantities, right? Structure becomes the standard circle coordinates centered at the receiver. SR. So SR is the transmitter. My fan version of the. Okay, so that's not. That is not very helpful at all. I hate when ancillary stuff gets messy. It's like my main issue is not getting addressed because all the ancillary stuff is just messy. All right. Kind of what we have there, right? So we'll just say that that's good. Okay. Additionally, the transmitter based transmitter receives a coordinate transformation. Why can I never ever spell this stupid word? Anyway. Right. Sure. Okay. So then. Right. Okay, so recompile. Okay. The next stage of what we need to do is oh geez, where did I have the other thing? No, it's over here. But that's not just simple, right? So we develop. Okay, so we said that. We said that. Okay, we got that. We got that. Right. The volume of integration V overall. This, however, only scatters within a single resolution cell. Volume DV can do significantly radar, right? But we don't care about that. Easy reverse location. it is worth noting that what was I just looking at? While cite these guys, restrict DV I'm sorry, restrict del R to be within a range bin bin standard radar range band, right? So that's restricting that to be within the kind of the range resolution of the unambiguous range resolution, I should say, of the radar. But that's not necessarily happening here, because we're not just looking at a radar that's bouncing out and back. We're looking at a system that's listening to a continuous radio signal and just kind of time integrating it over how long? Was it 1 minute or is it 30 seconds? I don't remember. I need to look at my data. Look at my data. Look at my data. Data. Look at my data. Sorry. I apologize. I don't know why anyone. Okay. Here we go. So. Jeez. I forgot. This is a giant freaking data set. Floor choice. Okay. 60-second average. The integration period of the high dive receivers is a full 60 seconds. Integration period, right? Because it's listening for 60 seconds and then computing a power from that. From which right, so it's got a full 60 seconds integration period. And it was, man. What? High dive data. High dive. Sure. Give me this. Okay. That's not helpful. That's not helpful at all. Okay. What is this? Of course. Of course it is. Of course. Okay. signal strength. All strengths taken. Mm-hmm. Right. Yeah. Okay. Which average signal strength is over which, I'm sorry, over which average signal strength is calculated. So given that we're integrating over a full minute, that means that it's the entire column essentially. This means that the entire right. So scatter volume. Here it is measure reflectivity of the effective scatter volume, which is formed by okay. For the antenna having an elliptical beamless, sure, the resolution cell can be approximately expressed as this. R squared delta R, theta 3 phi 3. Pi over 4R squared delta R. Where delta R is the range resolution, are the 3 dB beam width in azimuth and elevation, thus the RCS of the volume can be obtained by that. Sure. But what if we don't know the beam shape, or it's kind of an omnidirectional shape, right? See, this requires knowing the beam shape and stuff, right? To be able to calculate that. Sure. So, and then they go to Bragg scatter, which is true for the backscatter, but I don't think it's true for all scattering. Okay, I'm gonna be expressed blah 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 blah. Okay, so vector velocity. Um. Hmm. All right. Is beam column in the sphere is within the okay. Okay. Yeah. I think I'm gonna have to come back to this in a little bit. I've got some other stuff I need to get done, unfortunately. I was hoping that we could take this out and complete it, but that does not appear to be possible at the moment. In the meantime, I want to thank everyone who hung out with me while I was working and trying to figure this stuff out. It actually is fun to run through this and to try and pick apart and come up with these ideas sometimes. You know, even if it gets frustrating, you have to go searching and digging through all kinds of wacky stuff. Yeah, don't worry about it, Gothic. Seriously, there's never any requirement. This is just if you happen to hang out. Yeah, so I hope you guys have a wonderful rest of your day. I will catch you next time both of you stream. Yeah. Thanks again for coming by. I hope you have a good one, and I will see you all. The next scheduled stream is what is my next scheduled stream? Oh my god. How do I not know my stuff? Don't answer that. Don't answer that. Can I see my upcoming stream? What on earth is going on? It's not letting me see the upcoming streams. Of course not. I have upcoming streams at some point that are upcoming and will occur at some point in the future. Now I'm really curious. What's my schedule? what is life? Dude, I complete streamer brain. Okay, hold on. Also, why is my schedule thing not working? That's annoying. Okay, there it goes. All right. So the next scheduled stream is tomorrow. For reading, we have the next chapter of The Hobbit to read. So we will go ahead and do that tomorrow at 5:15 Eastern. Right? Today's Tuesday. Yeah, tomorrow's Wednesday. Okay. Dude, I have I don't know what day it is. I stopped knowing what day it was a long time ago. Anyway, yeah, so we'll be reading the next chapter of The Hobbit. We're getting close to the end there, and then we'll pick some other short stories or something to read alongside it to have a little bit of fun. And then we'll do, on Friday we have another scheduled heavy math stream. Maybe we'll do some gaming on Thursday or some other point in between then. In the meantime, thank you again for everyone who came here. I hope you have a wonderful day. I'm actually going to hit the stop streaming button this time. So I'll see you around the next stream. Goodbye.